Welcome to today's fascinating topic, the ice cream melting paradox. Why does premium slow-melting ice cream suddenly melt faster once it starts? Picture a scoop of premium ice cream. It's packed with tiny air cells, fat globules, and ice crystals in a delicate balance. The paradox is this. Premium ice cream starts melting slowly, but once it begins, the melting accelerates dramatically. Let's understand why. First, let's understand what makes premium ice cream different from regular ice cream. Premium ice cream contains three critical structural components that work together to create its smooth texture. Here we see air cells in blue, ice crystals in white, and fat globules in pink. These components are suspended in a liquid matrix of water and sugar. Air cells, also called overrun, occupy between 30 and 50% of the volume in premium ice cream. This is what makes it light and smooth. Ice crystals provide the structural framework and maintain the frozen state. Smaller crystals mean smoother texture. Fat globules, typically 10 to 16% by weight in premium brands, create that rich, creamy mouthfeel and help stabilize the air cells. The overrun is defined as the increase in volume due to air incorporation. Expressed as a percentage, premium ice cream has 30 to 50% overrun. Now let's understand why premium ice cream initially resists melting so well. At frozen storage temperature of minus 18 degrees Celsius, the entire structure is rigid and stable. The ice crystals form a rigid network, shown in white, held together by the frozen matrix, shown by these yellow connections. Air cells are trapped securely. The heat required has two components: sensible heat to warm the ice cream, MC delta T, plus latent heat to melt ice crystals, MLF. Sensible heat is the energy needed to raise temperature. For ice cream, the specific heat capacity C is about 2 kilojoules per kilogram Kelvin. Latent heat of fusion LF is the energy needed to convert ice to water at constant temperature. For water, this is 334 kilojoules per kilogram. The latent heat of fusion for water is 334 kilojoules per kilogram. This is a huge amount of energy, which initially slows melting. Let's do a quick calculation. How much energy is needed to melt just 100 grams of ice cream from minus 18 to 0 degrees? First, the sensible heat to warm from minus 18 to 0 degrees, 0.1 kilograms times 2 kilojoules per kilogram Kelvin times 18 Kelvin equals 3.6 kilojoules. Then, latent heat to melt half the ice content, about 50 grams, 0.05 kilograms times 334 kilojoules per kilogram equals 16.7 kilojoules. Total energy needed is 20.3 kilojoules. This large energy requirement is why melting starts slowly. But here's where things get interesting. There is a critical temperature threshold where everything changes. The critical threshold temperature is around minus 5 to minus 3 degrees Celsius. This is when the paradox kicks in. This graph shows melting rate versus temperature. Notice the slow rate below minus 5 degrees, then the dramatic acceleration above this critical threshold. At the critical threshold, the fat protein membranes surrounding air cells begin to soften and lose their structural integrity. Why does crossing this threshold trigger such rapid collapse? Three interconnected mechanisms suddenly activate together. The first mechanism is air cell collapse. This is the primary driver of the paradox. Air cells progress through three stages: stable when frozen, softening at the threshold, then collapsed as the walls break down. The pressure inside an air cell is governed by the Young-Laplace equation. Internal pressure equals external pressure plus 2 gamma over r, where gamma is surface tension and r is radius. Smaller air cells have higher internal pressure. This is why premium ice cream with many small air cells is initially more stable. But when the walls soften at the critical temperature, this pressure differential drives smaller cells to merge into larger ones. The surface tension of frozen ice cream is about 0.025 newtons per meter, but this drops rapidly when temperature rises. At the critical threshold, surface tension drops to about 0.005 newtons per meter, an 80% reduction. Let's calculate for a typical air cell with radius 50 micrometers at the critical threshold. The pressure difference is 2 times 0.005 divided by 50 times 10 to the minus 6 meters, which equals 200 pascals. 200 pascals might seem small, but it's more than enough to rupture the softened fat protein walls of the air cells. The second mechanism is a phase transition chain reaction. This is where thermodynamics becomes fascinating. When one ice crystal melts, it triggers neighboring crystals to melt faster. This creates a chain reaction cascade. Here's a critical question. Why does the melting of one ice crystal cause neighboring crystals to melt faster? The answer lies in latent heat release and changes in thermal conductivity. Let me explain. The thermal conductivity of ice is 2.2 watts per meter Kelvin. But the thermal conductivity of water is only 0.6 watts per meter Kelvin, almost 4 times lower. When ice melts to water, heat cannot flow away as efficiently. This means the melted region stays warmer. These warmer regions then accelerate the melting of adjacent ice crystals, creating a positive feedback loop. Heat flux Q equals negative Ka dt dx, where K is thermal conductivity, A is area, and dt dx is temperature gradient. With lower thermal conductivity K, the same heat input creates steeper temperature gradients, concentrating heat locally. This diagram shows how temperature gradients become steeper once melting begins. The transition from cool to hot becomes more abrupt. The third mechanism combines the first two, structural collapse acceleration through network breakdown. The network of ice crystals acts like a scaffold, holding the air cells and fat globules in place throughout the ice cream. When intact, the ice crystal network forms a strong lattice structure with air cells trapped at the intersections. As individual crystals melt, the scaffold strength doesn't decrease linearly, but exponentially. Scaffold strength S equals initial strength as 0 times e to the negative alpha F, where F is the fraction of melted crystals. When just 30% of the ice crystals melt, the overall structural strength can drop to only 10% of the original. This rapid loss of strength triggers catastrophic collapse of the remaining structure, and the ice cream suddenly becomes liquid. After collapse, the network is broken and disorganized. The structure can no longer support itself, leading to rapid melting. Now let's put this all together into a mathematical model that captures the paradox. We can model the melting rate as a temperature-dependent function that shows threshold behavior at the critical temperature. Below the critical temperature Tc, melting rate dmdt equals K1 times T minus T0, a simple linear relationship. Above the critical temperature, melting rate equals K2 times T minus T0 cubed times F squared, where F is the melted fraction. The cubic temperature dependence captures how heat transfer accelerates as the temperature difference increases above the threshold. The F squared term represents the positive feedback from the phase transition chain reaction. More melting causes faster melting. The critical temperature Tc is approximately minus 4 degrees Celsius for typical premium ice cream. Let's estimate the timescales. How long does the slow phase last versus the rapid collapse phase? The slow phase time equals sensible heat divided by ambient heat flux. 3,600 joules divided by 5 watts equals 720 seconds, or 12 minutes. But the fast phase, with enhanced heat transfer, takes only 334 seconds, or about 5.5 minutes, despite requiring more total energy. The fast phase requires 4.6 times more energy than the slow phase, yet happens in only half the time. This is the paradox quantified. What do real-world measurements tell us? Let's look at actual experimental data. This graph shows experimental data for premium ice cream melting at room temperature. Notice the clear transition around 12 minutes, when about 30% has melted. Premium brands with higher overrun show a much sharper transition at the threshold compared to regular ice cream with less air. Typical measurements show 0.8% melting per minute before the threshold, jumping to 3.5% per minute after. That's more than a 4-fold increase. Why is premium ice cream specifically more susceptible to this paradox than regular ice cream? 3 factors make premium ice cream especially vulnerable to the melting paradox. Premium ice cream has high air content at 50%, high fat at 16%, but relatively less ice at 34% by volume. Factor 1. Higher overrun means there are simply more air cells that can collapse, amplifying the effect. Factor 2. Premium ice cream has smaller ice crystals for smooth texture, but these melt faster once the threshold is crossed because of higher surface area to volume ratio. Melting rate is proportional to surface area over volume, which equals 3 over R. Smaller radius means faster melting. Factor 3. The fat network in premium ice cream provides less structural support than ice crystals, so when crystals melt, collapse happens faster. What are the practical implications of understanding this paradox? For consumers, understanding the paradox helps determine the optimal serving temperature for premium ice cream. The optimal serving temperature is -12 to -10 degrees Celsius, cold enough to avoid the threshold, but warm enough to taste properly. For manufacturers, this knowledge guides stabilizer selection and formulation design to delay or soften the threshold transition. Adding stabilizers, like guar gum or carrageenan, can strengthen air cell walls and raise the critical threshold temperature. Comparing formulas. Standard formulas have threshold at -4 degrees with rapid collapse, while stabilized formulas raise the threshold to -2 degrees and make collapse more gradual. There's a trade-off, though. Excessive stabilizers can affect the smooth texture and clean mouthfeel that defines premium ice cream. This paradox isn't unique to ice cream. Similar phenomena occur in other systems. Avalanches show similar behavior: slow stress accumulation in the snowpack, then sudden catastrophic release when a threshold is exceeded. Foam collapse follows the same pattern. Bubbles remain stable until the liquid fraction drops below a critical value, then rapid coalescence. Here is the corrected image for foam collapse.